me know. I will share it with you.
Okay, ma'am. Okay. Thank you, ma'am. Thank you so much, ma'am.
Oh,
Ma'am, can I get your mail ID, ma'am?
yes.
My
My
email ID
email
is
ID is
Yes, ma'am. Ma'am, I'll make a note of it. Yes, ma'am.
I'm
I'm
writing.
writing.
Okay.
Okay.
Have you noted
Have you
down?
noted down?
Yeah, tell me, ma'am. I have not noted. Where it is, ma'am?
It is
It is
Oh, in screen. Sorry, I'm not. AKSH. Akshita, na?
yes.
yes, right.
Akshita.
You can
You
raise a
can raise
Thank
a
you, ma'am. Thank
query
you so
on
much,
the
ma'am.
NPTL.
Pardon me?
You can
You
raise
can
a
raise
query
the
on the
query on the
NPTL,
NPTL,
Okay, ma'am.
and then you
and then
can
you can
clear your
clear
doubt
your doubt
regarding the
regarding the
assignment.
assignment and all this.
Okay, ma'am. Okay. Thank you so much, ma'am. Thank you.
Okay, now the screen is visible again. Is the screen visible again? Is the screen visible again?
Oh, yes, ma'am.
Okay, so I'm starting with the course now. Welcome all. Today we are in the third week of the course of nanotechnology, science and application. And here also we will be summarizing all the lectures as well as solve some conceptual problems and assignments of the previous week. I am Akshita Sharma from IT Delhi, uh, your mentor over here. So moving on to the next slide. First, we will discuss the previous problems of week one. So if you have any doubt in this assignment or any question, let me know. You can raise your hands and ask me the question. So in the first session, we have discussed what is the definition of a nanomaterial. Keeping that in mind, answer me that question number one. A nanomaterial is by definition a non-crystalline. Is it true or false?
Because all materials are having a crystal and both non-crystal. So, nanomaterial by definition it is not possible to be a non-crystal, ma'am.
Yeah, the definition of nanomaterial is different. By
Yes,
definition, we do
ma'am.
not define that is in a crystalline or in a non-crystalline, right?
Yes,
So it's
yes,
false.
ma'am. Yes, ma'am.
So then what will be the correct answer? What is a nanomaterial? If you have to define it,
Nanomaterial means it is up to the 10 to the power of 9 minus 9. That is either it will be a crystalline or non-crystalline. It can be a both. Like that we can tell, ma'am.
that is one of the features of nanomaterial. The definition of the nanomaterial is one of the dimension should be in the range of 10
Should
raised
be
to power 9
minus
meter.
9. Yes, ma'am.
Okay, one of the dimensions. So tell me,
Okay, ma'am.
I have a this structure which is in like 1 micrometer, and this side is suppose 10 nanometer, and I have another um, just wait, another smaller structure, say suppose this is 2 nanometer and this is 2 nanometer. Which of them is a nanomaterial?
First one, ma'am.
A or B?
Up to 10 to power of 9. Yeah, ma'am.
A.
Yes, ma'am.
Why not B?
Because in that first one is 1 nanometer and another one 10 nanometer. Because one of the dimensions should be
At
10
least
to
one
power
of
of
the
9.
dimensions should be in nano range.
Yes,
So
ma'am.
here both the dimension and nano range, so there is no problem. It is still a nanomaterial. If this can be a nanomaterial, so this also, then B can also be a nanomaterial, because two dimensions are nanomaterial, in nano dimensions. Are you getting?
So
Both of
then
them are
both,
nanomaterial. Fine. Is your doubt clear?
then both can be, yes,
Yeah.
ma'am. Yes, ma'am. Both
Yes.
can be a nanomaterial. Okay,
Yes,
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 ma'am.
both are nanomaterials. Moving on to the
Yes,
second
ma'am.
question. Due to the
Yes, ma'am.
presence of atoms, all material we use are nanomaterial. Is it true or false?
False only, ma'am.
Because we use bulk material also.
Yes,
We
ma'am.
have everything around in microscopic range. Everything is not around is a nanomaterial, right? So
Yes,
it
ma'am.
is false. Question number three. Diesel exhaust is an incidental nanomaterial.
True only, ma'am.
Okay. What do you mean by incidental nanomaterial?
Because we are only producing that one.
Yeah,
Incidentally, it
but
is produced
it is
by
a
exhaust.
consequent of some reaction process which is not in the control of our hand. So it is an incident. So that is
Yes,
why
ma'am.
it classified into the incidental nanomaterial. So it is true.
Yes, ma'am.
Question number four. Chemical precipitation is a top-down approach for synthesizing nanomaterial.
This one, it is a bottom-up approach. So it
So,
is false only.
right, false. What is an example of top-down approach? If chemical precipitation is bottom-up approach,
Top down means bulk material is using ball milling or some of the process we can make the particle into small particles. That is top down approach.
yeah, so ball milling is one of the examples.
Ball milling.
Another example of bottom-up approach, another
Um,
synthesis process.
okay,
There were
ma'am.
two, three examples in the lectures. One was chemical precipitation. There were two other methods.
Uh, bottom up approach na
Any other
இது
example of,
butter
yeah,
condensation chemical precipitation homogeneous
oh,
pebbles.
sorry?
No, 1 minute, ma'am. Example bottom
Yeah,
condensation process, ma'am.
yeah, right. Condensation process. Evaporation and condensation process.
Evaporation. Yes, ma'am.
Another example of top-down approach, apart from ball milling,
Turning turning into balls, grinding, ma'am. Grinding, mechanical grinding.
um, your answer was not clear. Pardon. Okay, I'll explain. It is chemical
Yes, ma'am.
vapor deposition. Okay,
CVD,
this is
ma'am. Chemical
also
vapor
a
deposition.
yeah. We will study about this process
Top
in a
down
bit
approach.
detail in upcoming slides, and I will explain you how does it work and how we say it is a top-down approach. Okay?
CVD also top down, ma'am.
Yeah. CVD is top-down.
Okay, ma'am. Okay, ma'am.
Question number five. For the same decrease in the size of an animal, its weight decreases than its surface area. True or false? Like we have a same. Uh, it was an in the lecture. The example was an of an elephant. So
Elephant and deer.
yeah. So on basis of that approach, answer this question. For the same decrease in the size of an animal, its weight decreases faster than its surface area. True or false?
True only, ma'am.
Weight decreases faster than its surface area, right? True.
Yes, ma'am.
But why does the surface area uh, is more than its weight when we decrease it? Is it becoming nanomaterial or is it still in a bulk range?
The surface area shrinks when we decrease the size of an animal.
No, surface area increases because
Surface area
more
increases, but that
because
shape
because
shrinks.
because more of the atoms are exposed to the environment. So that way
Okay,
surface area
ma'am.
increases.
Okay, ma'am.
Okay, so this is
Okay,
true.
ma'am. Okay, ma'am.
People have made nanomaterials for near 500 years. True or false?
This one actually true, but I kept a false, ma'am, because 1959 only they have invented, na, so I thought by calculating 150 years,
In
like that I
19
thought.
in 1950 they have discovered it.
Oh,
There was a talk. Okay, but the nanomaterial existed
that's
since
why,
the
ma'am,
ages.
that little bit I confused and I kept
So
wrong for that, ma'am.
so it is true.
Okay, ma'am.
The
I
carbon suits, the carbon particle which we used to put on our eyes like kajal, it was there since ages.
yes, ma'am. Okay, I
Okay,
understood, ma'am. Okay,
so it was this we came to know about it as a nanomaterial, but it was still there. So it is true.
yes, ma'am. Yes, ma'am.
Wood steel from Tamil Nadu contained carbon nanotubes.
True only, ma'am.
True.
Yes,
Okay.
ma'am.
What are carbon nanotubes?
Carbon nanotubes, these are all the materials that can be used as a nanomaterial, like damascus steel, like that. Some of the particles we can use, ma'am.
Uh, does carbon nanotube look like this? Is it a spherical in shape or is it a sheet-like structure?
Sheet-like structures, ma'am.
Or is
2D
it
materials
tube-like
like
structure?
that.
Which of them is correct? A, B, or C?
B, ma'am.
No, B is wrong. Carbon nanotubes are cylindrical in shape. They're in nano
Okay.
range. So this area, cross-section area is in nanometers. Okay, and
Okay,
the
ma'am.
length can be in micrometer range also.
Okay, ma'am.
So that are carbon nanotubes. The sheet-like structures are called graphene,
Oh, sorry, I
and
confused.
this spherical is carbon dot,
Okay,
and
ma'am.
this is carbon nanotubes.
Okay,
Do you get
ma'am.
the difference?
Yeah, okay, I understood, ma'am.
Then, question number 8. Discovery
Yes.
of nanomaterial has been limited by the magnification of electron microscope.
This one only I confused, ma'am, because
Now you
I
know
kept
the
the
answer of question
first.
number 6. Okay.
Yes, ma'am.
Then now uh, think and answer it. Discovery of nanomaterial has been limited by the magnification of electron microscope.
False, ma'am.
Yeah, false. The
But I
electron
kept it
microscope
true that time.
came into the picture after a very long time, but we were able to know that yes, these are nanomaterials.
Yes,
Okay,
ma'am.
because their
Yes.
properties were different, their optical
Yes.
properties were different, their mechanical properties were different.
Yes.
You have seen examples of like Damascus glass, this wood steel in the lectures. So we were able to discover it
Okay, ma'am.
without the using any electron microscope.
Okay.
Question number 9. A person who is 1.5 meter tall,
Yes, ma'am.
what is the value in the 10 raised to power 6, sorry,
6 is
nanometers?
missing. Yes, ma'am.
Uh, it was 6 or minus 6?
10 to power of 6 only, ma'am.
Okay, so what is the value?
Answer is 1500, ma'am.
Yeah, right. Because 1 nanometer is equal to 10 raised to
10
power
to power of
9
minus 9.
meter.
Ah,
So using this, we can get the number.
yes, ma'am.
Any doubt till now?
No, ma'am. Clarify, ma'am.
Okay. Now we have come into the week 2
Yes,
assignment.
ma'am.
In his talk, there is a plenty of room at the bottom. Feynman discusses writing on the head of a pin using a sharp pen.
Actually, this was true only, ma'am, but that answer they kept false. While his discussion, he will tell like plenty of rooms at the bottom, like that he will tell.
Uh, Sorry, what are you saying?
He will tell that
Yeah,
there is plenty of rooms in that. It is
yeah, that
true
was a
only now.
title. Okay,
Okay.
but has it discussing the writing using a pen?
Oh, with coding only he told.
With coding and
Uh,
with material, but not with the sharp pen, right?
oh, yes, ma'am.
The Richard Feynman did not talk about any sharp pen in his talk, so it is false.
Okay, ma'am.
He was talking different other techniques to write.
Yes, ma'am.
Question number 2. The talk looks at the possibility of writing information at a small scale without any coding.
This one also, with the coding, I thought like that I kept true, but after that only I realized without any coding, it is not possible to write now. So it is false only.
No, it is
Answer
true.
is false. Huh?
It is not false. We can write without coding, right? What does Richard Feynman meant by coding? Coding he meant like in digits of 0, 1, like in binary form.
Bit, okay.
But we were he also told about uh, he also told about that we can write with the using AFM tip. He was giving the example of a cantilever in the lectures using a sharp tip
Cantilever.
and making
Pin
and
like that.
making
Pin
and
head.
making
Mm.
some valleys in the shape of the material in the shape of the word we want. Are you following me?
No, in cantilever like that he mentioned. I'm just thinking.
So let me explain it again.
Yes,
So without coding, it was also possible to write. Like we can take a sharp tip of an AFM
okay.
and create using that very sharp tip of a nanometer range. We can create some valleys.
Okay, ma'am. Okay.
Okay, in the shape like if you want to write I, then we will create the cavity in the shape of I,
Okay, ma'am.
and then fill up the space with some material which is visible to our eye, like some pigmented color, okay, of that material,
Okay, ma'am.
and then we
Okay, ma'am.
able to read and write both
Okay,
without any
ma'am.
coding. Coding, he suggested that if you want to write more, like if in the on the same space, if you want to write more of it, so coding uses less space than writing I A B C D alphabets, right?
Yes, ma'am.
So that was he meant. So it
Okay,
is
ma'am.
true.
Okay, ma'am.
Question number 3. A major challenge in miniaturizing computer is the heat generated in thinner wires.
True only, ma'am.
True.
Yes, ma'am.
Because nanomaterials get heated up very fast and loses heat instantly. So that is why
Yes, ma'am.
using nanomaterials in the thermal application, uh, it is not a good approach. So it is true.
Mm.
So it is a challenge. Question 4.
Yes, ma'am.
It is likely to be difficult to sustain ignition in extremely tiny engines due to the significant heat. Okay, sorry, I have read. It's the same question. It is likely to be difficult to sustain ignition in extremely tiny engines due to the significant heat losses involved.
True only, ma'am.
Yeah. Question number 5. At very small scales, van der Waals forces can resist gravity.
True, ma'am.
True. Because the tunneling of current which we talked about is one of the example that the van der Waals resists gravity.
Yes, ma'am.
Okay.
Yes, ma'am. No, pardon me. 1 minute, ma'am. 1 second, ma'am. Van der Waals.
Forces can resist gravity at very small scale.
No, no. That explanation what you have told, ma'am.
The example I gave you in the week one session, the tunneling of current, it does not
Tunneling of
require
current.
it does
Yes,
not
ma'am.
require any medium. So
Okay,
it
ma'am.
comes from the it loses electron from one of its metal and then passes on to the other.
Okay, ma'am. Okay.
Okay. Question number 6. Activation energy barrier makes many non-equilibrium phases stable.
False.
What do you mean by activation energy barrier?
Because it is the one makes the material stable. Stable.
So that is what the question talks about now. The activation energy barrier makes many non-equilibrium phases stable. So we
So it
see,
is true only. Yeah.
I
Okay.
have one of the reactants and some chemical processes going on. This is the
Okay.
activation barrier and this is the product. Reactants
Okay.
are on this energy. This is the energy profile and this is reaction coordinate. This can be any parameter like number of moles, time, anything. Okay. This is we are concerned about here only energy profile. So this is suppose we have 20 kilojoule over here. Here we have 10 and here we have around 35 kilojoule. So here the phases are the reactant and products are stable that you know. But at this higher energy, the phase which is formed is get stabilized because the energy barrier. They are non-equivalent phases like we have suppose this is A interaction. I have two reactant A and B. What happens here in the activation energy barrier? A dissociate into single particle, similarly B, and then it slowly forms some attraction forces with A and B.
Okay, ma'am.
This bond is breaking, and this bond A and B bond is forming, bond formation. Now product becomes A, B. So this phase gets stabilized here. So this is a non-equilibrium phase.
Okay.
So it is true.
Okay, ma'am.
Our common experiences, our common experience with the stability of material is often related to the kinetics of reaction.
True, ma'am. Our common experience with stability
Or
of
common
materials is
false.
often related to kinetics.
Okay,
False.
because
Okay,
kinetics
ma'am.
is related to the speed, rate of the reaction, not the stability.
Okay,
Okay,
ma'am.
so that
Yes.
is why na. So if we have carbon in the environment, we have oxygen also, but
Okay,
not
ma'am.
all the
No.
carbon nearby us get converted into CO2. Even though the CO2 is a stable, thermodynamically stable,
Yes, ma'am.
but it required that activation energy barrier, which is related to the kinetic part of the reaction.
Okay,
Okay,
ma'am. Okay, ma'am.
so that is why it is false.
Okay, ma'am.
Microstructure of a material include the phases present.
Microstructure. True, ma'am. Microstructure of a
Microstructure of a material
material
include phases present.
plus phase is present.
We have no, it's false. Microstructure is not related to any like phases. We can have single phase. We can have multiple. Microstructure means it is not in the nano range, but it is in the micro range. Okay, you are
Okay,
able to
ma'am.
see the things. it is
So
not
if
related to phase, na? Whatever phase it has. Suppose I have calcium oxide in micrometer range. I have calcium oxide in nano range. The phase is same.
okay,
It is
ma'am.
not.
Okay, okay,
It does not get affected. That is in micro or in nano. The phase
okay,
remains same.
ma'am. Okay, ma'am.
False. Question number 9. Phase diagram indicate the kinetics of the associated reactions.
True
True
only,
or
na?
false?
False. Phase is only presence. It tells phase changes. So false only.
Um, what does phase diagram indicates?
Phase
If we have
diagrams
a
it
phase
shows.
diagram, uh, we discussed about the phase diagram of nickel and copper in the lecture, right?
Yes, ma'am.
So, what were the relation between the phase diagram?
Some alpha solid liquid phase is present like that.
So, here
In
is
which phase?
temperature and here is the moles. Okay, fractions like how much copper will form alloy with a nickel. Okay, here are the moles. The phase diagram is related to the temperature and the composition or pressure, but it is not related to the kinetics of the reaction.
Okay.
Are other students following? Rishabh, are you following? Following me? Some students have joined. So here, students, we are discussing week 2 assignment and we are on the last question who have joined recently. So question number 10. Phase diagram help us determine relative amount of the phases present. True or false?
True only, ma'am.
I have explained you what is a phase diagram over here. So you can answer question number 10. True or false?
True only. True only, ma'am.
Other students, is it true or false? If you have any doubt, you can ask me the question. So it is true. So we are done with the assignment and now we will move on to the questions of week 3. Zirconia as an example to thermodynamic properties of nanomaterials. So here we will discuss the zirconia, how its thermodynamic properties changes in bulk or in nanomaterial when it comes into nanomaterial. Fine. Formula of zirconia is it the zirconia which we are discussing here, is it ZrO2 or Zr2O3? Which is the correct formula? A or B?
Yeah, ma'am.
Right. So, what is the common name zirconia is known as? What is the common name for zirconia?
Zirconium oxide. Zirconium oxide.
Common name like which we usually use in day-to-day life. Yes, American diamond.
American.
Why? It is known as American diamond. As American diamond. Simple, because it shines like a diamond. Okay, that is simple. It is very shiny. It reflects light as much as better than diamond because cut the cuts are very crisp and nice. Okay, and that is why it is cheaper also. It is not the diamond which formed inside the earth crust with high temperature and pressure. Okay, it is an artificial diamond. That's called American diamond. So this is a next question is a multiple select question. That it means that uh, one option can also be right or multiple option can also be right. So question is, in which phase or phases zirconia oxide can be crystallized at various temperature? Is it cubic, tetragonal, monoclinic, or all the above? We will understand these terms what is cubic, tetragonal next slide, but for the information that how have you understand the lectures or not, so for this sake answer me which is the correct option. Anybody? You can write your answer in the chat box. I won't mind if you are unable to speak. So the correct option is all the above. The zirconia oxide crystallizes in all three forms, in all the three crystal system, cubic, tetragonal and monoclinic, but the temperatures are different. Okay. So at room temperature, it is present in which crystal system? Is it cubic or
Monoclinic, ma'am.
monoclinic? Right. Then tetragonal comes crystallizes at what temperature?
Around 1170 something.
Monoclinic. Yeah, it is around 17, like 170 degree. What about cubic?
2370.
Yeah, 2370, and the range can be like it is stable in the range of 2370 degree to 2680 degree. Okay, so these are the temperature that transformation takes place. Any doubt till now in this question?
No,
I
ma'am.
hope. Yeah. So the next question. This is a very interesting question to understand. Here you see an image. You see that I have a zirconia matrix like ZrO2 matrix, and there is a crack. This is a crack initiation, and slowly it is present in a tetragonal phase. Okay, it is an example that zirconia is already present in a tetragonal phase. But when cracks happens, the early stage of crack propagation you can see it propagated to the another end of the matrix. Can you see? Are you following me? It is slowly propagating to the another end. And finally, the later stage of the crack of the propagation is about to reach the end, and it has now slowly replaced the tetragonal particles into the monoclinic particles. See the color change. The green one are tetragonal particles. Here the orange one are the monoclinic particles. So can anybody explain that why this change happened? I understand that this crack is a would have been possible because there was a temperature drop, because tetragonal is stable at 1170 degree Celsius. So the crack developed because there must be some temperature drop. Obviously, because monoclinic phase is stable at the room temperature. So that is why crack generated. But why did it went into this structure? Monoclinic. What happens in the on the what is happening at the fundamental level? Anybody? or shall I explain? So what happens when we move on to monoclinic to tetragonal? There is a around 3 to 4 volume, or like maybe like not 3 to 4, at least 5% volume decrease. Fine. So the crystal system is strained. The volume is decreasing, right? But the atomic size, the atom size remains same. So there is a strain in the molecule, in the system. And now it is cubic over here. Fine. But when this crack is generated, it is generated because it want to lose its stress, it want to lose its strain. Then what will happen? It will try to increase its volume because it has got more space now, and therefore when it move on to, so it want to lose its strain. So to lose its strain, it needs more volume, and more volume it finds in the tetragonal to monoclinic transformation. Here there is an increase around 3 to 4% volume increase. Have you followed this example? Any doubt, or shall I repeat this example again? If you are fine with the problem, you can give a thumbs up, or if you have any doubt, you can raise your hands. It is a very interesting example. Shanam?
Ma'am, can you please once again repeat, ma'am?
Okay, that is why I'm asking. So this is an example. There is a crack is generated in a tetragonal zirconia matrix. Okay, matrix means that it has a zirconia particle in tetragonal crystal system. Have you followed this?
Yes, ma'am. Yes, ma'am.
Okay, so I am saying that crack must have been generated because there is a temperature drop, because tetragonal is stable at this temperature. So maybe the matrix was cooled down to room temperature. So that is why crack has been generated. So question was that why it is going back slowly into the monoclinic form. Here you can see the orange particles are slowly increasing, which refers to monoclinic particles. So the answer is that from monoclinic to tetragonal there is a volume decrease. Okay, that is why it has been propagated. The initiation was must have been through temperature, but the propagation, the driving force was that the tetragonal molecule particles are strained because the volume has decreased. So it want to lose that tension, that strain in its system. So it expands, and there is a volume increase when it changes into tetragonal to monoclinic, and the change is around 3 to 4%. Is that clear?
Okay, ma'am. Clear, ma'am.
Okay, so that was an example. Next question. Which of the following match is incorrect in respect to lattice parameters, angle and crystal system? You have to tell me which of the match is wrong out of these four options. Do you follow me? That is it. For when we define cubic, other lattice parameter are these is A is equal to B is equal to C, and alpha, beta and gamma angles are 90 degree. Is it right or wrong? Right. Okay, Aditya has given up the thumbs up. Anybody else? Are the cubic parameters are matching with the one in the question? Yes. Orthorhombic,
Yes,
I will
ma'am. Correct,
explain
ma'am.
what are the features. In orthorhombic, all the angles are 90. So this is wrong. What about monoclinic? Is this relation between the parameter and angle is correct or incorrect?
Correct, ma'am.
No, it's wrong. I will explain it. Okay? In monoclinic, one of the angle is not 90. So the parameter which you are seeing here in orthorhombic is actual the parameters of monoclinic. And the orthorhombic parameters are these. Okay? Do you follow? All sides are not equal, or all the sides are not equal, but all the angles are 90 degree. Tetragonal. Is this match is right or wrong? Anybody else? Aditya has given the response.
Yes, ma'am.
Is it correct?
Correct, ma'am.
Yeah, it is correct. Aditya, the answer for the tetragonal is right. One of the two parameters are same, like A and B parameters are same. C is not equal to A or B, but the angles are all 90. Okay. So to understand better, I have shown you some the 7 crystal system which we have. So isometric here means cubic. Okay. Don't get confused. So from the previous question, tell me, are all the sides equal for the cubic? Am I right or wrong?
Yes, ma'am. Yes, ma'am. Right only. All sides are
What
equal.
about the angles? Alpha, beta, gamma. These are the angles. Alpha, beta, gamma. What do you see? Are they 90 or not? Just see the figure and answer me. Are the all angles 90? This is an interactive session, students, so you have to interact so I can explain you better. You will able to understand more if you answer the questions. So are they 90? Yes, they are 90. Now see the tetragonal, see the figure, see the sides, and tell me what are the relation between the sides. This is A side, this is B side, this is C side. Is A is equal to B or not?
Not equal, ma'am.
See the figure. A and B are equal, right? See the figure. A and B are equal. C is not equal to both of them. Both of them. C is much more lengthy, much more longer than A and B. It can be shorter, but is not equal to A and B. So the relation develops like this. What about angles? Alpha, beta, gamma for the tetragonal. See the figure. Are all angles are 90? This. Yes, other students. Aditya has Aditya is saying that they are 90. Do you all agree with Aditya? Yes, 90. See the figure and then understand that. Yeah, right. Rishabh is also saying yes. Now, orthorhombic. What about A and B and C parameter? This is A, this is B, this is C. Are all of them equal, or do you say that they are unequal? all three parameters are unequal to each other. Yes, see, B is smaller, A is little bit longer, and C is the longest. These in I'm not saying that C is always longer. It can be shorter also. But the point is all should be unequal. All all the axial length of the unit cell are unequal in the orthorhombic. But are the angles 90 or not? Orthorhombic. Yes, they are 90. So till here, in orthorhombic system, from cubic to orthorhombic system, all the angles are 90. Now comes monoclinic. Yes, yes, Shamu Gavi. Yeah, you are right. I'm sorry if I'm pronouncing your name incorrect. Pardon me. Monoclinic system. Now see the parameters. A, B, C. Are the parameters equal? Are the parameters equal in monoclinic system? Rishabh, see the diagram carefully. Can you are is A side is equal to C side? Is the length of A side is equal to C side? No, there is a difference in the length. In monoclinic system, all the three A, B, C parameter are unequal. Okay. So if you follow the trend, if we are moving from cubic to monoclinic, there is a drop in the symmetry. Here all the sides were equal. Here one of the side was unequal. Here all the sides become unequal. So if we are moving from left to right, the inequality in the parameter persists. So that you are able to understand better. Okay, from left to right, symmetry in the parameters is decreasing because inequality between the parameter is increasing. Are you following this? So in monoclinic system, all the three parameters are not equal. What about axial angles of monoclinic? Do you see any 90-degree angle in monoclinic system? Yes or no? In monoclinic system, there you're not seeing any of the 90-degree angle. What is the perception of the 90-degree angle? That you have a two straight perpendicular lines. So there there any perpendicular lines? Yes, there are two 90-degree angle. This is a 90-degree angle. This is a 90-degree angle. So there are two 90-degree angle, that is alpha and beta 90. And this angle which is a little slant over here, it is not equal to 90. So we tell it gamma. Gamma can be less than 90, more than 90, but it is not equal to 90. So that is the characteristic of monoclinic system. What about triclinic? Are the parameters equal or unequal? Are the parameters equal or unequal? Anybody else? Do you all agree with Rishabh? Sorry, Aditya. He's saying all the parameters are unequal. Are you able to see unequal parameters? Shanu Gavli? Yes, right, unequal. All the parameters are equal in triclinic system. What about angles? Do you see any 90-degree angles in triclinic? Do you see any 90-degree angles in triclinic? Come, if you are unable to recognize the exact form 90 degree, compare with the tetragonal or cubic system. Do you see that? Do you find any 90-degree angle between cubic and triclinic? Compare this 90-degree angle with one of the angles of triclinic. Yes or no? Does triclinic system have, crystal system have 90-degree angle? Answer in yes or no. No. None of the angles of triclinic crystal system is 90 degree. So not the parameters are same, not even the angles are same in triclinic. Okay. Hexagonal crystal system. This is A parameter, this is B parameter, and this is C parameter. So tell me, is this relation right for the hexagonal system? The relation which I have written. Aditya is saying no. What about others? Rishabh is saying no. Shamugali, C. This is a C parameter. Do you find C is equal to A? No, it is longer. So C is not equal to A. And see here A or B are similar of length. So A is equal to B, but B is not equal to C. This is the relation. Do you find any 90-degree angles? Yes, there are two 90-degree angles. Here are one 90-degree angle, here is another 90-degree angle. But this angle over here is this is equal to 90 and this is equal to 120. Hexagonal. The name suggests like the outer angles are 120. This is 60 and outer angles are 120. So common sense. Trigonal system. What about the parameters? This is A parameter, this is B parameter, this is C parameter. Trigonal system are a bit different from all the other systems. So parameters are such like that A is equal to B and B is not equal to C, or can be equal to C also, because no, sorry, all the three parameters are same, but due to the image is a bit incorrect, so you are finding C is longer. But in the trigonal system, A is equal to B, B is equal to C, and angles are alpha, beta, gamma are less than 120 but not equal to 90. This is a condition for the trigonal system. The conditions for the trigonal system are that alpha, beta, gamma are less than 120 degree, but they are not equal to 90. And the parameters are all same. Do you follow all these 7 crystal system? 1, 2, 3, 4, 5, 6, 7. Do you understand the relations between their lattice parameter, their axial angles like alpha, beta and gamma? So now I think you follow this question correctly, that the cubic is a correct match, orthorhombic is an incorrect match, monoclinic is an incorrect match, and trigonal is a correct match. Yes, good. So here you see the examples. Okay. See, these are the examples of natural occurring minerals. So you see fluorite. This is a cubic. When it is not polished or cut, so if you see in real life, you will find that it has actually crystallizes in a cubic form. Okay. Fluorite means calcium fluoride. It is cubic. The actual shape is cubic. So see, the crystal system can be cubic, but the shape can be anything. Do you follow? Shape can be anything. Irregular shape, spherical shape. The shape can be anything. But there are some minerals which has a shape of their crystal system. Okay. So this is crystallizes in cubic system and it forms a shape of cubic. One of the example is fluorite. Do you understand this part? Yes or no? Okay, good. I hope other students are also following this. Another mineral, wolfenite. It is lead, molybdenum, O4. This is a chemical formula and it crystallizes into tetragonal. Okay. These are minerals. Tessonite. The chemical formula is, it is a bit longer, calcium, aluminium. It has a silicon group, O4, thrice hydroxide. It crystallizes in orthorhombic. If you bit cut in a proper shape, then you will get these kind of shape, actual shape. So that is why it is a very typical example. Okay. Azurite. It is blue in color, so one of if it is a general perception, or you can find it is like a thumb rule that blue color means it has a uh, it is a copper related chemical compound. Copper thrice carbonate hydroxide. So it crystallizes in monoclinic system. Amazonite. What is the crystal system? You see that this Amazonite is one of the, in all of the 7 examples, it is bit irregular. You don't find any particular shape. You see some kind of shape over here. You see some kind of shape over here. You also see some kind of shape over here. You also see some kind of shape over here. Do you find any shape in this Amazonite? Yes or no? Just see the things. Do you find any kind of shape over here? Some pattern? Yes or no? Like here you find a bit facet like cubic structure, square shape like six structure. Here are some square shape like structure. Do you see any kind of particular shape in this Amazonite? Amazonite belongs to, yes or no? Answer it. Potassium, aluminium, silicon 308. No. Yes. Right. So what was a crystal system which does not have any similarity or any pattern follow? Go back. Triclinic. Triclinic did not have any parameters equal to each other, any angle equal to each other. None of the angle was 90, none of the lengths were equal. So that is why it has such a irregular shape. So this is triclinic. This is very well understood. What about this emerald, which we use in gemstones? What is the crystal system? You can see the shape is very much clear and familiar to you. What is the crystal system? Emerald has a chemical formula: beryllium, aluminium, silicon, 3O, 436. Yes, right. So, do you follow the purpose of this example? To see the shapes. What about rhodochrosite? Rhodochrosite. We have left with one, and the name also suggests. Rhodochrosite. It belongs to trigonal, which sometimes it is called rhombohedral also. Okay, trigonal is also called, with some conditions change, rhombohedral also. So the name suggests rhodochrosite. It is Mn, it is manganese carbonate. Do you follow all these examples? Moving on to the next part of our questions. So these are now typical questions which requires your participation. What is the application of YSZ? Before that, answer me, what is YSZ stands for? In the lecture it was discussed the full form. First tell me the full form and then the
Yes.
application.
It is yttrium oxide.
It is related to yttrium, yttria, stabilized zirconia. Okay. So YZ stand for yttria stabilized zirconia. It means zirconia has, this is a formula of zirconia. Okay. We have substituted some yttrium, which we represent with Y, into the system of zirconia. So we can, I will explain the details in the second question. So it is called, so this is known as yttria stabilized zirconia. Application of yttria stabilized zirconia is, where do we use that? Hint is, it is used in some energy storage devices. I have given you the hint. Now answer me the application part of it. It is, the application is solid oxide fuels. Fuel cell. Yeah, fuel cells, solid oxide fuel cells. Fuel cells, we have fuel cells which use gaseous systems also, but here the application is solid oxide. Okay. So now the question is, what do you understand by yttria stabilize? So this will answer our second question, how vacancies are generated. If you see the zirconia example, here the oxidation state of zirconia is +4. Zr, it is Zr. The yttrium oxide which we dope has oxidation state of +3. If we doped, you know what you mean by dope? Dope, that we replaces some zirconium atoms with the yttrium. Yttrium. even if even if we dope 1% also, then we have some imbalance of positive charges, because for the 4 oxygen we require, for the plus 4 oxidation state of zirconia, we have 2 oxygen atoms. But here, when we are doping plus 3 oxidation state yttrium, it required 3 atoms, not 2. So there will be charge imbalance. To balance this charge imbalance, what happens that some oxygen vacancies get generated. Okay, what happens that two zirconium, what happens in fundamental level, that one yttrium molecule, one yttrium atom replaces 2 zirconia atoms. Got it? So it required 2 zirconium atoms required how much atoms? 4 atoms of oxygen. And one yttrium atom is required 3. Got it? So there is a decrease in oxygen atoms. This decrease oxygen atoms, that the atom which is less, on that site is called vacancy, because it is vacant. Are you following this? Answer in yes or no. I'm answering your question, how vacancies are generated. Good. What about other students? Okay, if you have any doubt, you can raise your hand. So I'm moving forward. So this site is called vacancy. Fine. And what happens? This vacancy is generated. So when it is used in application, like thermal application or any electrical application, obviously thermal and electrical application require electrons, and electron find its space in vacancy. Okay, and this vacancy, and there are multiple vacancies generated. I have given an example of only 2 zirconium atoms. So multiple vacancies are generated. There are multiple space for all electrons to travel through YSZ material, and that is why it is used in such application, like in electrical energy storage application, electrical application, thermals application. All this deal with electrons. Got it? I'm explaining in very basic and simple language. There are much more technicalities, but since this is a basic course, so I'm explaining in very basic manner. Followed? Done? So do you understand what is YZ? Why it is used in the application part? I hope this is clear. Next question. Next question is zirconia property in the following application. So these are the application I have mentioned, like zirconia is used in artificial teeth. It is used in non-allergic content and in turbine inlet also. These are the some application. You have to tell me what property I'm utilizing over here. If I am using zirconia as an artificial teeth, then what property I am using of zirconia? Teeth have strength, so that is why you're able to bite things, chew things. So here the strength, yeah, biocompatible is also one of the answer. Here we are utilizing strength and biocompatible properties of zirconia. Okay. Similarly, non-allergic content, we are utilizing biocompatible property of zirconia. Turbine inlet, okay, I will explain you. In turbine, that like we have a wing-like shape of inlet, and zirconia is coated over this inlet, and this is used in very high temperature conditions, maybe about up to 1000 degree. So what property? So I have explained you the application of turbine inlet. Now tell me the property I'm utilizing over here. I have in the previous slide I mentioned three properties: thermal, electrical, energy storage. So what a property I'm utilizing in turbine inlet if I'm dealing with temperature? I'm using thermal property. Yeah, thermal barrier. Why Z is a thermal barrier in turbine inlet, but the property I'm utilizing is thermal property because at these high temperature, why is SZ is not it is not degraded, it is not decomposed. You also know, na? It is we are able to it sustain it around two cubic crystal system up to 2370 degree. So 1000 is sufficient for YSZ to does not decompose. Okay. Next question. How grain size affects zirconium oxide optical properties? How grain size affects zirconia optical properties? So the answer which I expect you from people that answer me if I have a large grain size. So zirconia is transparent. If I have a small grain size, is it so it means it is opaque? A or B? Are both the statements are right? If zirconia particles have large grain size, does it imply that it has transparency? Is it right? The answer I expect in this form. Yes or no? Is the A statement is correct or incorrect? I know this is a very bit difficult, but you can both are correct. Aditya is saying both are correct. How many of you agree or disagree with Aditya? Rishabh is agreeing. What about Shanam Govli? I'm sorry, like to mispronounce your name. So all the three students agree with each other and saying that if I have a large grain size of zirconia, it has transparent properties. Interesting. It is very random, so don't find that I'm making a pattern in this. One or two. Which one of them is a large grain size? Which one of them has a large grain size? One or two? One has a large grain size. Yes. One has a large grain size, okay? So it means 2 has a small grain size. Now we need to understand, does large grain size give transparent properties or opaque properties? Here, uh, like understand in a very basic manner. I am reflecting light. It has a large grain size, but number of grains are smaller. Do you agree? Large grain size, but numbers are less. It implies that the reflection of the light, internal reflection of the light inside this particle will be less. It can easily pass through it if we compare with 2. And if someone is able to pass through, then it gives a transparent nature. Okay. Similarly, which has a small grain size, grain sizes are small, but number of grains are more. Internal reflections will be high because the grains number of grains are higher in case of 2. Internal reflections will be more. Light will not be able to come out, pass through it easily, and it will give opaque property, opacity. So that is why this example of large grain size zirconia transparent is of American diamond, which shines like it, and the small grain size of opaque is an example of artificial teeth. Okay, so the bulk nature of zirconia is used in American diamond, and nano range which has small grain size is used in artificial teeth. Did you follow these applications? I hope I've I've connected you all the properties of zirconia with nanomaterial. Yes. Any doubt? I hope there are not any. Good. Now next questions we will discuss a bit questions on as zirconia oxide as oxygen sensor, MOSFET, and solid oxide fuels. This is related to your lecture, so it is a direct question. What is the operating temperature of zirconia if when used in oxygen sensors? Oxygen sensors are used in cars to monitor um, combustion of fuel and oxygen ratio. Okay, this is the purpose of an oxygen sensor. To monitor this, zirconia is used. So the question from you students is that combustion of fuels happens at some temperature. So it happens at some higher temperature. As you see, the activation energy is higher. And zirconia is stable at higher temperatures. We all agree with this. We have established this. So what temperature we used such sensors? What is the temperature from on that we use sensors? Operating temperature. It is a very direct question. It is operated around 300 to 400 degree Celsius. Okay. It is an application based question. Next question. What are the operating voltages for minimum and maximum oxygen content used in zirconia based oxygen sensor? I've explained you the purpose of oxygen sensor. It is used to monitor combustion of fuel, air, Okay, air, oxygen from air is utilized. So tell me, what is the voltage? What is the voltage? What should be the voltage of oxygen sensor if the sensor want to give you the information that it has used maximum amount of oxygen? If sensor has to give you the feedback that I have used most maximum amount of oxygen to burn the fuel, then what should be the voltage value it should you should see on the feedback system? Your options are 0.2, 0.5, 0.45 or 0.1.
0.1 month.
Right. What about minimum? What was the value, if you all remember? What was the minimum value to tell you that the fuel has not been combust properly? 0.9. Point 0.9, right. Okay, you follow this question?
Yes, ma'am.
Okay, thank you. Next question. Configuration of N or NP type semiconductor in zirconia based MOSFET. MOSFET is a field emission transistor. Which option is correct? Shaman Gavli is saying PNP junction is the right answer. Do you all agree? Is it not one? Which option is right? One, two, three, four. Which one? Other students. Option 4 is correct. It is P type, not N. No, option 1 is not correct. Here, P type junction are used here, and in and the middle N type junction is there, and above this zirconia is deposited or is there, and a metal contact is over here. So this type of configuration is used in MOSFET transistors. Okay, these questions can be asked in your examination, so I have picked up and framed the questions on the basis of lectures. Okay, these are very typical questions. Now one of the interesting part of the session. Here we will discuss, in this question we will discuss the reversibility of the phase of zirconia at nanoscale. And also, if you are talking about phase, then we should know about the temperature also. Till now, what we have studied, the bulk phase of zirconia says that it convert monoclinic to tetragonal to cubic from room temperature to around 170 to around 370, like some values were like this. But if I'm using nanoscale, nano range ZRO2, then does this phase change stands? Do you think that same transformation will happen at nanoscale? Do you all agree? Yes or no? Will same kind of transformation like from monoclinic to tetragonal to cubic will happen at nanoscale level also? Yes or no? Aditya is saying no. What about other students? Yeah, obviously not. If the things would have been same, then we will not. So we will not be studying zirconia or nano material in such a detail. So the purpose, you have to understand the purpose of this course. The purpose of this course to introduce that some things are different at nanoscale levels and some things are different at bulk or micro level. There is some change in the properties, and that is why we need to need to learn this field. If the thing would have been same, then there was no need to study. If we are studying, so it means the uh, phase reversibility, so, or some phase change would be there. Thermodynamic property would change at nanoscale. To understand things but better, you see this equation. This is one of the most and widely used equation, thermodynamic equation. So delta G is the Gibbs free energy. Delta H is enthalpy of the reaction. T is the temperature. And delta S is entropy. Okay. This equation is used when we dealing with the bulk materials. Which are bulk materials means that materials are not in nano range. Any of the dimension is not in the nano range. We use this equation. But when we talk about things at nanoscale, then these temperature remains temperature. There is no point. There is no such change in entropy because ZrO2 was there at bulk level also, and ZrO2 is also there in nanoscale also. The chemical formula composition remains same, so there is not much change in the delta S. But there is a change in the delta H part, and the change is like when we move on to the nanoscale level, new term get introduced. This was the surface energy, and this was the surface area. I hope I'm correct. Okay, so this term get introduced. So when this term is get introduced, the whole term, there is a whole change in the delta H, and when there is a change in delta H, there is a change in delta H. Delta H, there is a change in delta G, and delta G is related to the stability of the material, thermodynamic stability. Do you follow this? And thermodynamic stability, I told you when I gave you this example of crack, it was unstable when crack was generated in tetragonal. So it moved on to much more free, much more better space which has increased volume and monoclinic because the data was monoclinic. So because there was volume increase, it was stable and it has changed into monoclinic. So here also the stability matters, and that is why nanoscale the monoclinic system will not be stable, but another system will be stable, that is tetragonal. And what is the beauty of this nanoscale level, that it does not require any temperature conditions. Like this all transformation happens at room temperature. In one phase we require temperature difference to change from one phase to other, but here at room temperature the stable phase is tetragonal. Okay, so this this fact has been experimentally proven, and this is the paper you can find. Energy cross, you can read this paper, this is freely available on the internet. Energy crossovers in nanocrystalline zirconia. Okay, and it was studied in 2005 by these scientists. Main part of the story is monoclinic zirconia. I have highlighted this part if you're not able to read it properly. Monoclinic zirconia was found to have largest surface enthalpy, and amorphous zirconia has the smallest. Stability crossover with increasing surface area between monoclinic, tetragonal and amorphous zirconia were confirmed. When when we went on to the nanoscale level, there was a difference in the surface energies of monoclinic, tetragonal, and amorphous, and was found that till, till certain level that monoclinic has the highest surface energy. And I will explain this figure later. First, move on to this part. So you can see that when it has just begun, the monoclinic had least surface energy, hence the least delta H, sorry, least H. Lesser the H, lesser the enthalpy value, better is the stability. This is the thumb rule. So here till here part monoclinic system is stable. But as we move on to the surface area has been increased. That surface area has increased because we are moving towards the nano level, nanoscale level. And now the tetragonal phase has become stable. Okay, see here at same surface area, monoclinic has lower energy. Like if I go more, see if you see this one here, tetragonal has lesser energy and monoclinic has more energy. Lesser energy means better stability. So that is why tetragonal becomes stable. And when we move on to increase surface area, like suppose this one. So at this value, amorphous has lesser energy as compared to tetragonal. Tetragonal has this energy and this monoclinic has this energy. Are you following this graph? Say yes or no. Are you
Yes,
following
ma'am.
this plot? Okay. So when we move on to more nanoscale level, amorphous 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 nature of the zirconia becomes stabilized. Do you get it? And this all happens at room temperature. The room temperature zirconia, if you move on from bulk to nano, these transformation you can happen. There is no required of temperature. Okay, so that answer your question. Explain the reversibility of the phase at nanoscale and what are the temperature conditions. One more thing, one interesting thing is that just for your information, they have calculated the values. Delta H value, as you see, 10.6 kilojoule per mole. Delta S value, 13. It is around one. How much is it? 7.3 mole uh, per mole per joule per mole per Kelvin. See the units. You can be asked what are the units. In the exam. Okay. See the units properly. So these are the real values of this transformation. You can go through these paper and other scientists have also found some values. So you can see how the values changes of from zero point 0.7 to 22, from -20 to -34. Such a wide range for different temperature conditions, for different crystallized size of zirconia. Got it? Now this is small question which I have explained you in the previous lectures also. To revise over here, to confirm that, first they are claiming that they have synthesized nanocrystalline zirconium. They are claiming that they have synthesized nanocrystalline zirconia. Okay, what is the proof that it is nano? How will you come to know that it is nano? What is the specification? What are the dimensions? We use electron microscopes. Okay, in week 2 we have studied about tools to study to see nano things at nano level, so we use electron microscope, and this is the TEM, transmission electron microscope. And see, the scale which has given is 5 nanometer. This means that if you take this measurement as 5 nanometer, then you can find out this length is somewhat equal to this length. This is 5 nanometer. This is a bit lesser, so it can be around 4.5 nanometer. So you can confirm from this scale that the particles are in nano range. Do you get it? Do you follow? Yes. Okay, this is a TEM image, and how do they confirm that is a nanoparticle? From this scale, and using this scale you can find out the dimensions of it. So that is why it is a nanoparticle. Just a quick question. Next question. Which method is to be followed to reduce the large grain size of a metal sheet? If I have a thick metal sheet which has a large grain size, obviously thick metal sheet have a large grain size. I want to decrease the I want to I want to have small grain size. Then what process should I follow? Only rolling? It is incomplete. It is cold rolling. Okay? In the cold rolling, when you cold rolled a metal sheet, you can have a small grain size particles. As simple as that. So, what is the how do you classify this cold rolling? Is it a bottom up approach or a top down approach? Is it a bottom approach or a top down approach? We are moving from large grain size to small grain size. Right. It is a top down approach. From higher to lower. So it is a top down approach. Second question. What do you meant by recrystallization temperature for metal? What do you mean by recrystallization temperature? You can see it is related to your previous question only, that I'm going from crystallization. I'm moving from large grain size to small grain size. I'm moving from large crystallite size to small crystallized size, from bulk to nano size. Okay. Now tell me, what do you mean by recrystallization temperature? What is the definition? It is the answer is in the previous question only. So these questions have been designed so you are able to answer the future questions, the upcoming questions. That is why they're in a particular order. As the way the lecture progresses, I have developed and designed the question the same way. So recrystallization temperature means the temperature at which the large grain size is changed from a small grain size. It moved from bulk to nano range. Okay, there's a reformation or a redesign. Okay, redesign of the crystallize and grain size. Okay, is it related to melting point? The temp. So answer me. The temperature at which the recrystallization happens, does it related to the melting point? of the metal. This case is true for metal. We are the context of these two questions are metals. Yes, Aditya is saying yes. What about other students? Is it related to melting point? Yes. How? What is the relation? How they are related? I have a recrystallization temperature. I have a melting point. How they are related to each other? What is the relation? The relation is that the recrystallization temperature is of metal is equal to this around zero point 0.4 or 0.3, yeah, 30 to 40%. Okay, these this can vary. So if question come in the exam, you will be given information that which value you have to take. Okay. Next question. Differentiate between the below mentioned bottom up approaches. This is an example of bottom up approach. We are synthesizing nanoparticle using this approach. But what difference do you see? There is some difference you see. There is some difference you see. What is the difference? It means both the processes are different. Name the process. Name this process. Name this process. Name the process. Name this process A. Name this process B. This is usual evaporation and condensation. Okay. The particles, this is a substrate which we have, like bulk substrate. Suppose we have gold. The electrical current is passed. The metal is vaporized because the ionization energy matches. Okay. Ionization energy matches with the electrical energy passed through it. So they rise above. They found a cooler substance which is not that high temperature, so the particles cool down on this on this substrate. This is a sample. This is we call sample or target. This is our substrate. The particles cool down over here, so evaporation and condensation. This process is called sputtering. Everything is very much same, but to here we don't have any control. Particles will be randomly will randomly crystallize in whatever nanoscale. They can be, some particle can crystallize in nanometer, 5 nanometer, some can crystallize in 10 nanometer. Here we have no control. But to control the kinetics, to control the size, we introduce some gas. Mostly it is argon gas. Argon gas is ionized in this chamber, and this and then particles uh, follow or follow through the substrate using this mediator. Okay, these are also specific size particles, and that is why with some, since we have control, we can increase or decrease the flow of the argon gas, and we can get some control over the crystallized size. 6 to 7 nanometer we can get using the controlling the flow and the speed of the argon gas. Okay, so here the kinetics of the synthesis of the nanoparticle is controlled. So it is sputtering, and this is usual evaporation and condensation. So we have solved this question. Next question. Statement 1. This question is related to the hardness, Wixer hardness, which we have seen in the lecture. So you have to tell me which statement is correct, or both the statements are correct. The way you have to answer this. Statement 1 is Wixer hardness. Wixer is a Wixer hardness number of a material is dependent upon the load. Load means the weight. You understand how the Wixer hardness is measured? We put a load on a material, some load on a material. We use some instrument which is of a diamond. That is a statement 2. The test involved the indentation of an angle of 22 by the diamond shaped pyramid tool. Aditya is saying both the statements are right. Does everybody agree? Both the statements are correct. Both the statements are correct. Okay. But now you have to answer, is statement 2 is the correct explanation for statement 1? The angle which we use of 22 degree is dependent upon the load, or is it independent of the load? Answer that. Is statement 2 is the correct explanation for statement 1? Right. It is independent. So statement 2 is not correct explanation of statement 1. This is a numerical. 10 Newton force is applied by load which makes a square of length 12 millimeter. Calculate Wicker's hardness. Wicker hardness process formula is force by area. Here the force is 10 Newton. You have a, what is the area we use over here? We use area of the diagonal, the square which forms, we use the 2 by d square, that is the area. You have 12 mm, 12 mm. You have to find the diagonal. What is the diagonal length? And use in this formula of 2 by d square. Put that value over here. For your kind information, the d will be around 16.9 or 16.7 mm. You have to put that value over here. Okay. It is in Newton. The unit for the Wixer hardness is kilogram per meter square. Okay. So convert the Newton into kilogram. 1 Newton is around 0.97 kilogram. So 10 Newton will be, apply your unitary method and solve this question. Do you follow? Will you able to solve this question, or shall I solve it? Do you follow the solution? Yes. Other students, do you follow the solution? Okay. What is the next, moving on to the next question, what is the validity for Hall patch effect for bulk material? You understand what is the Hall patch effect for bulk materials? The Hall patch effect for the bulk material is, you can explain by this graph, that if you move on from around, if you have range of 5 micrometer, say up to 25 micrometer or 30 micrometer, it increases. So the strength or the hardness increases. That is the Hall patch effect for the bulk material. What is the validity? This relation is valid in what conditions? Right. The particle should be more than 1 micrometer. Got it? So these type of questions can come in the statement form. Okay, and you have to answer such questions like statement 1 is correct, or statement 2 is correct, or this explanation is correct. Okay. So such questions or statement can come. So validity is 1 micrometer, should be greater than 1 micrometer. Why the properties of nanomaterial are dominated by their grain size? Very simple question, very simple answer, but very technical answer. Why properties of nanomaterial are dominated by their grain size? Because at nanoscale level, with the boundaries, the total, these boundaries at nanoscale level, suppose we have 5 nanometer, and these boundaries can be of 1 nanometer, so it matches with the range. The size of the nanoparticle matches with the grain size, and that is why the properties, whatever the properties nanomaterial have, good thermal properties, bad conducting properties, it can be anything, it can be good, bad, anything, better, worst, best, but that all will be depend upon their grain size. Grain size, or I mean grain boundary, not size, boundary. Got it? I think we are on the last question. Okay. What do you understand by term eco-cohesive temperature? Eco-cohesive temperature means temperature at which the temperature below which the grain boundary are stronger. Okay. So it give hardness to your material, or above which the grain boundary are weaker. So the same material at different temperature will give you different strength. So that temperature is called eco-cohesive temperature. Fine. Next question. Explain inverse Hall patch effect. Inverse Hall patch effect come from the nanomaterials. For the bulk material, the relation was like this. This is a crystallized grain size, and this is strength. We have a uh, direct relation but with some slope. In inverse Hall patch effect, suppose we have 5 micrometer and we have 25 micrometer. When we increase the grain size, strength also increases. But in at nanoscale, if we increase the crystallite size, the size of the particle, the strength decreases. Okay, we have some slope over here, some sorry intercept, positive slope, negative slope. Follow? What do you follow this? So that is why it's called inverse Hall patch effect. So the overall Hall patch effect will be the combination of these two plot. Okay, the combination of these two plot for bulk and nano level, we will able to get overall Hall patch effect. Last question. Explain the equation and its significance. You have to explain the terms. What is this term? What is this term? What is this term? What is this term? And significance you have to explain for the D, T only, temperature and crystallized size. So what is this? So what is this belongs to? Who will answer? This is strain rate. This is some prefactor or some constant depending upon the material. This is, what is this? What is this A? What does this mean? Who will answer this? Aditya? We are on the last question, so kindly cooperate. What is sigma? What is omega? This is area. This is some diffusion coefficient of grain boundary. This is Boltzmann constant. This is temperature. This is hardness, I think. Look for what is this delta equals to. Okay. This is grain size D. So the significance is that if we decrease the grain size, as we know the relation is inversely proportional, so the strain rate will increase. Okay, but smaller increase in the grain size will increase the strain by 3 by by thrice, like not thrice even, by cubic times. Okay, 10 d raised to power 3 is the relation. So even if a small strain, the decrease in the grain size will increase the strain rate by many orders, by up to 3 orders. What about the temperature? Temperature is also in the denominator. So from the equation we see that if we decrease the temperature, we will have increase in the strain rate. But it is not so. As we have seen in the lecture that this uh, diffusion of grain boundary is dependent upon the exponential power of temperature, which is in the numerator part. So increase in the much more impactful in the numerator part, and hence increase in the temperature will increase the strain rate, and this factor will not matter. Do you follow? This is the last question. Do you follow this? Yes or no? And then we can finish the class. Okay. I hope your doubts, your assignment questions, everything was clear in this lecture. We will see the next assignment in next lecture, week 4, and solve the question like this only. If you have any doubt, we can discuss in the next class. Thank you.